In order to understand periodic trends or trends on the periodic table, we need a good understanding of two concepts. Nuclear charge, which is the charge of the nucleus by the protons, and we'll call that, we'll indicate that with Z. And then the shielding effect. I'm going to use argon to illustrate these two concepts. Argon has a nuclear charge of 18. It has 18 protons, and in a neutral atom, it also has 18 electrons. Two of them are going to be found in n equals 1, the 1s orbital. They're not in these circular paths, but just to simplify this illustration, we know that they're in clouds of probability, and then in n equals 2, we got 2 in the 2s and 6 more in the 2p, but I'm just going to draw a few of them here. And then in n equals 3, there's 8 more. Right, but again, I'm just going to draw a few of them just to illustrate this concept. Right, so I'm going to use these blue arrows to show you the relative magnitude of the attraction between the electrons and the nuclear charge. So these two electrons in n equals 1 are feeling the greatest attraction for that nucleus, those 18 protons. It's right there in front of that action, and there's nothing impeding them. They're the most tightly bound to that nucleus, or attracted to that nucleus. Now, electrons repel other electrons, so they are going to shield the electrons outside of them. So the electrons in n equals 2 are feeling less of an attraction to that nucleus because they're being shielded by 2 electrons closer to the nucleus. So for those electrons at n equals 2, they're seeing about an effective nuclear charge, a Z effective, about 16 protons, because 2 out of the 18 are being shielded by the electrons in the 1s orbital. All right. Now those 8 electrons in n equals 2 are also shielding the electrons outside of them. So the electrons in n equals 3 are feeling the most amount of shielding. So they're farthest away, but they're just all being repelled by the inner electrons. And not only that, they're seeing much less of the nucleus because of that, so they have the least attraction. That's why when you ionize electrons, it's the outer electrons that are first lost. So at n equals 3, those are your 3s and 3p electrons. They have a Z effective, or they're feeling a Z effective, an effective nuclear charge of about, there's 8 in the second and 2 in the, so they're seeing about 8 protons each. They don't shield each other for the most part. Now, it is true that the s orbitals do shield slightly if you look at the radial probability distribution. And then there's something called orbital penetration, which, let's just stick with this here. There's, what was I saying? So, the s orbitals do shield the p's slightly, but for the most part, these electrons on the same energy level, they do not shield each other. Let's just say that to simplify this. So now we can take a look at a few trends. Let's take a look at, let's say this is energy. And we have hydrogen with 1 proton. It has 1 electron. Let me draw this a little higher. In the 1s orbital. So how do you measure radius, right? In these particles that don't have discrete boundaries, so that they're not like billiard balls, like Dalton said, but rather they're clouds of probability. So you can take a bond length And you can do these with these diatomic molecules, or even if they're not diatomic, you can get the average bond lengths of these things bonded to other stuff. Right, but this would be like hydrogen, H2. So you can take the bond length of that molecule and get half of that bond length. That's one way to measure the atomic radius. All right. Well, it turns out this thing, hydrogen, is about 30. It's about 37 picometers. So what do you think? As you go to the right, well, the only other element on that first period is helium with 2 protons. So it's got a greater nuclear charge. Where do you think helium's electrons are? Do you think they're farther out or closer into the nucleus? Well, hopefully, if you understood what I said just a few minutes ago about nuclear charge and shielding, these electrons don't, in hydrogen or helium, they don't experience any shielding because they're right there in the first energy level. They're going to be closer to the nucleus because the increased nuclear charge. So it turns out, let me go this way. Turns out helium has an atomic radius of about 32 picometers. Right, so the trend here is as you go to the right, atoms get smaller. Okay, let's go down the period to period number 2, where we have lithium. Oh, could have done that. All right, so there's energy. Just draw it out again. All right, lithium has a nuclear charge of 3. Has 3 protons. So the 2 electrons in the 1s orbital are definitely going to be closer than any of these guys because of the greater nuclear charge. But now they're going to shield. I'm not really sure how to draw that. They're going to shield any electron outside of it. So lithium does have 1 electron outside of that in the 2s orbital, and that's going to be shielded by the electrons underneath it. So it's going to be farther out. So this is like 152 picometers. Because the atomic radius is from the valence electron to the center, and this guy out here is being shielded by the two underneath it. So that electron has a Z effective, is feeling an effective nuclear charge of only about 1 proton, right? Because the 2 electrons are shielding about 2 protons each. All right, so let's do the one next to it. Is beryllium. So why don't you predict where the 1s electron is going to be in relation to lithium? Well, hopefully you're saying they're closer to the nucleus. Let's go there. All right, because let me keep that, match these colors. It has an extra proton. So those 2 electrons are going to be closer. All right, and then let me make this a little bit clearer. And then those valence electrons are going to be closer than lithium's valence electrons. Right, so hopefully this one is obvious. That's closer because you've got an extra proton. Now these guys are also closer because they do not shield each other. So these 2 electrons are feeling about the same amount of shielding as that valence electron from lithium's, which is 2. Right, you got 2 electrons shielding in both cases. But this here has an extra proton attracting in those electrons outside. So I don't really know how big a beryllium atom is, but I know it's going to be smaller than a lithium atom. There's the trend. Now if we go all the way to the right, we're going to skip all these elements and go all the way to neon. Neon is going to be the smallest. I'm sorry, that has 8 protons there, but total of 10. So neon is the smallest because it has 10 protons, and those 2 electrons are as closest of all of these examples because there's nothing shielding the inner electrons, and that n equals 2. All right, well, here's the 2s, and then the 2p, or maybe a slightly higher. All right, so any one of these is seen about, the Z effective for any one of those n equals 2 electrons for neon is seen about 8 protons, whereas this guy, for lithium's valence electron, the effective nuclear charge was about 1 proton. So you can see why neon is so much smaller, because these 2 guys are shielding, but there's 8 more protons that they're not shielding. So the atomic radius for a neon atom is about 69 picometers. It's much smaller. So there's the trend. Now let's talk about, so the general trend on the periodic table for atomic radius, or radii, is as you go down the periodic table, atoms generally get larger, and that's because of the shielding effect, the greater shielding effect, because you're adding more layers of electrons, and electrons repel each other. All right, so even though you have a greater nuclear charge going down, it's just the shielding effect is the primary factor. So atoms get larger. As you go to the right, atoms get smaller. Oh man. Atoms get smaller, and atoms get smaller because you have the same amount of shielding, but there's more nuclear charge. All right, you're adding protons, so the Z increases going to the right. So they get pulled into the nucleus. All right, so the overall trend for atomic radius is, as you go left and down, as you go down and to the left, atoms, neutral atoms, generally get larger in size. Now there's hiccups, of course, but that's the general trend. Let's take a look at one other thing. Let's take a look at first ionization energy. So first ionization energy is the energy required to remove an electron from an atom in its gaseous state. So to remove this guy is going to require, what do you think, more or less energy than to remove one of these guys from helium? Well, helium's valence electrons are closer to what they're attracted to. It's going to be harder to remove helium's valence electrons than it is hydrogen. So it's going to take about 1,300 kilojoules per mole of energy to ionize hydrogen's 1 valence electron, versus it's going to take about double that, about 2,370 kilojoules per mole to ionize one of helium's first valence electron. Now, so the trend is, as you go to the right, because those electrons are closer to what they're attracted to, ionization energy increases. As you go down the periodic table, those valence electrons get farther and farther away from what they're attracted to, so they become easier to remove. So you would expect it to be much easier to remove lithium's valence electron, because not only is it farther away, but it's also being shielded by two core electrons. Turns out it takes only about 520 kilojoules per mole to ionize lithium's valence electron. Now, finally, how much energy do you think it would require to ionize one of these guys? Well, it'll be from the P, but one of these guys. Neon's valence electron. Hopefully you're thinking it's going to take more than lithium, but less than helium. Okay, it's going to take more energy than lithium because they're much closer into what they're attracted to, and they're each feeling a much greater effective nuclear charge. But it's going to be less than helium because helium's electrons are even closer to the nucleus, and they're not being shielded at all. So it's going to be about 2,000. Let me actually look this up. All right, 2,080 kilojoules per mole. Pretty close, but a little less. So your overall trend for, let me zoom out on this so you can see all corners there. So the overall trend for ionization energy, the general trend, is as you go up and to the right of the periodic table, it requires more energy to remove those valence electrons. We call that ionization energy. Specifically, the first ionization energy to remove the first electron from an atom. Right? Again, as you go up, those electrons on the outside are closer to what they're attracted to, and as you go across the periodic table left to right, there's greater nuclear charge and the same amount of shielding.